Today we are going to finish up airside in 3 weeks because I'm missing the next two. May 1, May 8, I'm out of town. But the next one, we're going to start mechanical refrigeration. Now, airside. When I say the term return air path, what comes to people's mind? Champ wet. That's not wrong. Yeah.
Is the air coming back to the air handler?
That's even better. Yes. You know, we spend a lot of time focused on the supply system. You know, the duct velocity so that we don't get rumble and it's fairly efficient and yada, yada, yada. But we don't spend frequently enough time thinking about the return. Now, if this is a one-story building and I got a rooftop unit here, there essentially is no return. I put some kind of an egg crate or some kind of a grill, anything I want in the ceiling, and it just sucks it out of the ceiling because the rooftop unit is sitting there right above the unit, or right above the cavity, right? That's simple. The longer it goes, though, the more involved it becomes. Often, I will see consulting engineers design projects with 3 and 4 and 5 and 6-story buildings with open ceiling return, but it's got to get up to the roof. And so there's a shaft that comes down for the return air, and it just pulls air at each floor out of the ceiling. Consultants will often put balancing dampers on those shaft openings. I can understand what they're thinking, but that is an example of wasted money. As long as you design the supply to get where it's supposed to go, and you don't hinder the return air, it will find its way back home. Think about that. So, I've got multiple stories, I've got a supply system on the top, I'm pulling it up through the back. As the air comes into the floor, it's going to want to pressurize the floor, isn't it? Because we're pumping air in. It's like blowing into a paper bag. And as we pressurize that floor, the air is going to want to escape. Where is it going to go? Return that. You know, it's going to go into the ceiling, but from there, it's going to escape because when you're blowing up that bag, you're blowing up not only the occupied space, you're blowing up that open ceiling return plenum above the plenum because they've just got a couple of grills, they're open to each other. So as you pressurize the occupied space, you're also pressurizing the ceiling. And it will then get pulled right on out of the ceiling to go wherever it was supposed to go. Now, how many of you guys are familiar with a conversion curve? So, the curve of a rooftop unit probably looks something like this. And we talked about, you know, furring it in on the, how the roofer would, but we didn't talk about what sits on the top. Typically, if this is the roof opening in here, we've got an opening here for, I don't know, a supply. And an opening in here if it's a down shot, on the other side maybe for a return. You all know that supplies have X's and returns have slashes, right? What's an exhaust duct have? What's the symbol for an exhaust?
A slash with 1.
A slash with 1, yeah. If this is a supply duct looking in the plan view down, and if this is a return duct, an exhaust duct looks like that. Or maybe it's like that, I never can remember. But it's the combination of the two, okay? So, we've got a return and a supply to our rooftop unit. And this curb is made to have an opening here and going across to the top of the curb and opening here. And then there might be a complete cover here if you're worried about weather covers, and just an opening there. Or they might rely on the rooftop unit itself to make a seal, in which case there'd be nothing there and you just have this and that, you know, up to the top level of the rooftop unit. Okay, well, when you go to replace that rooftop unit 18 years later, and the new unit doesn't have the exact same openings for supply and return, the cheap thing to do is what's called a conversion curb. And that's a second curb that you sit on top of the first curb. And the second curb's got an opening in the top part of it that fits the new unit, and an opening in the bottom part that fits the old unit. Which one do you think they try to line up the most closely, the supply or the return? Supply is true. Now why?
Less resistance.
You want to minimize the static pressure impact, the system effect, right? You don't want to be messing with the discharge right off the unit. You don't want to be messing with it. So what you'll typically do is you'll find that they will take the new unit, they will set the new unit in a way so that the supply is still pretty darn close to what it was before. And if they've got to put the return over here, or then it doesn't matter. Whatever that new unit needs is fine, because again, like we said at the beginning, as long as you don't severely restrict its path, the return air will find its way home. Now, a conversion curb will add some static pressure drop to the system. You would have less static if you just scraped that old curb off, put a brand new curb on the roof that was designed for that unit. But if you did that, you're going to have to change the ducts down below to fit up, right? And you're going to have to re-roof. So there's a huge cost difference between scraping the old curb off and putting a new curb on, as opposed to sticking a conversion curb on it and making the unit this much taller than it was before. And so you're going to see both things out there, but on onesie-twosie replacements, what you're going to see are conversion curbs. So that was our little conversation about return air. Now, if I use the term open ceiling return, what does that mean to you guys? No what? Well, open ceiling return, okay, no duct. No return duct. What if I say open ceiling supply? That means there's no ceiling. Now, if there's no ceiling, and you can see the supply duct up there, what's different than if you actually had a ceiling? Give me some differences, because there's several. How is
just in the conditioned space?
How is a ceiling supply diffuser mounted in a ceiling system?
In the grid.
It's in the grid, right? And you've probably got some hanging wires to help with the weight. Okay. If there's no ceiling, where are the supply diffusers?
Directly on the duct.
Directly on the duct. Or maybe if it's way heck up in the air, you dangle down a duct a little ways and then you put one. Yeah.
So it may be, it may not have like flex duct connections
Usually won't.
because it's all solid and the grills are.
Usually, yeah, because it's supporting the. Yeah, that's another difference. You're going to have flex usually for the last ways to hook in a ceiling. You won't have flex if it's exposed. And so exposed supply duct work, flex does a couple of things for us. One is it covers up sins in terms of not having things exactly where we intended, because it's easy to move around and hook up. But what's another thing flex does for us?
Sound attenuation.
Yes. I've heard lots of people say the right answer that time. That's correct. So what does that tell you? In an exposed duct system, brand, it's up there, you can see it. What does that tell you about the acoustical issue? Depends is a good answer, but we don't have the ceiling to act as somewhat of a sound attenuator, right? It's not there. We don't have any flex. So should there be a little more concern about what the sound might be? Yeah, I would say yeah. Normally people do some things with some velocities. If you're using spiral is pretty good about being relatively quiet. But if you've got flat duct, and you might say, well, if it's an exposed duct system, I'm usually using spiral, and that's probably true. Usually you probably are. So that wouldn't be too bad. You know the most common noise complaint that we get in VAV systems that are exposed? It has nothing to do with air noise. Yeah.
Oh, exposed? No, yeah, I think so.
The most common noise complaint we get is the hot water valve on the reheat coil. As that thing opens up and closes, there is going to be a difference in the water noise sound. What would you guess would be a fairly effective way to minimize that?
Decrease the velocity of the water in the pipe.
That's one way, sure. You may also be able to adjust the speed that the valve opens and closes. Almost every sound problem you will have is going to be made better if you slow it down, as opposed to making it really abrupt. Okay? So that was talking about open ceilings, exposed, yada yada. Ducted returns. So, it's 1991, and I'm in charge of commercial over at what is now US Air, and back then was SCACD, which was the carrier distributor then. And a really common application for us was 2- and 3-story buildings where, I'll just draw a 2-story, but the same was true for the 3. You'd have a fan coil in the ceiling, you'd have some chase that you could run DX pipe, you got a condensing unit on the roof, and you got however many zones of these fan coils you got on the ground floor. And then the upper floor, because it was cheaper, would be a bunch of little rooftop units that were like this. If they were real concerned about sound, they didn't do this. They would do side discharge. Because if you're standing here on the second floor, the only thing between you and the return duct opening on that unit is the ceiling. Is it okay? Well, maybe it's okay. A lot of buildings have been built this way. The majority are built this way. But if this is an owner-occupied building, and they're going to be in the building, and of course they're going to be in the second floor office because that's where the owner of the building is, maybe instead of this, you do this. Because acoustically now, you've got and it's a little more static pressure because we've got to come out, got to make a bend, got to go down. But this is lined duct, and it will attenuate the sound depending on the piece of equipment you got. That return air duct opening is probably just the other side of a filter and a cooling coil from the compressor. Or, excuse me, from the fan. It's probably not far. It's the other side of a little piece of sheet metal from the compressor. So, and the condenser fan. So it's not the optimum quiet thing to use a downshot if there's going to be somebody right under it who's going to be picky.
Can I ask how have you typically seen those configures? Is it just a straight duct plugged into the ceiling, or did they put an elbow on it? Is it sized at 500 feet a minute? Did you put 2 elbows on it? Sound doesn't like going around right-hand corners.
Good point.
There's ways to defeat that.
So if you're going to do this, you could come down, you could have a duct with a couple of L's, you know, and it could be lined, and once you were down out of the initial opening, you could make this bigger and cut down on the velocity. There's a lot of things you could do, but the more things you're doing to this, the more cost you're adding to the down shot, and now you're starting to make the side shot maybe a little more competitive. Just think about the side shot. The general contractor is going to have to get the roofer to do a second roof penetration here, and there's going to be some cost associated with that. And you're going to have some outdoor exposed duct, which is going to cost more than whatever you would do down in here, right? So it becomes one of these things. There's also a question of, do I use a spring curb on this unit? That'll help you a little bit. It's an order of magnitude thing. It's how many bullets do I want to shoot at the target to try to make sure I kill it. But the standard standard retail, if this was a strip center retail application, you could stand here, pop the ceiling tile, and you'll be looking right up into the return air. Every Costco you ever went to, you could look up there, and granted, it's way the hell up in the air, but you would see a return duct sticking down with a screen over it so the birds don't fly into the unit.
They're not concerned about sound.
Well, yeah, but they're not real concerned. But the other flip side of that is, bear in mind, even though a Costco is concrete and metal, basically, it is way up there in the air. That helps. And you've got tables and tables of jeans and stuff to help absorb sound. So, you got to take it in the context of where you're putting it as well. Okay. Okay, the last thing that we didn't talk about, job like this, one giant open ceiling return. How many of you guys have sat on the other side of that wall where Rich sits and listened to everything that went on in this room? Rich has. What is this level of sound privacy if I'm in this room and I'm not just whispering, and I'm not capable of just whispering? Todd's worse, but I'm not very good about this. And if I'm just talking quietly, even if I'm just talking quietly, if I've got a return air opening here, and there's, this wall doesn't go up to structure, and Rich's desk is right there, and he's got a return air grill, don't you think he can hear pretty much everything I say? So sound privacy in an office environment might be kind of important. You might have people who don't want everybody listening to their phone conversations with their client. Attorneys, this is a prime example. They get all wrapped around the axe handle about sound privacy. Investment advisors often get this is a huge thing. Exam rooms in a doctor's office, these are all huge things where sound privacy is important. That doesn't mean that you necessarily have to run the wall up to structure and start penetrating walls and doing all that stuff. There's other things you can do. What's the easiest thing you can do? Well, you could duct it, yeah, but even easier than ducting it. What would you do to the return air grill if you wanted to make it a little less sound transmission oriented? A boot. A boot.
I was gonna say add a piece of flex or something to it.
Okay, so if you're the service technician, you're coming in after the fact and you just want to do something to kind of make it better. Yeah, you could hook some flex right to it, run it over here a ways, and that actually works reasonably well. So this is a trick question, what does a sound booth look like?
An elbow.
At the minimum, it's in hell. And what's it made out of?
Sheet metal and insulation.
Sheet metal and insulation. What about ductboard? It's cheaper and that works. What if you want to do something a little more? We put a sound booth in at Fox Studios inside the recording studio where the people sit there and they get interviewed and the news people get up there and the camera's on them. Well, over in the corner is their server room. And like every IT group on the face of the earth, they kept putting more servers and more servers and more servers into the racks That meant they had to have more and more supply air. We finally ran out of available supply air, so then we had to put an exhaust fan in the room, spring, flex, to blow it out. But they couldn't, in this studio environment, they couldn't be hearing the server room, because you guys have all heard, you get enough of those little muffin fans going and it's pretty audible. So we put a sound boot on it. But we had to get it right the first time. So we were conservative. Our sound boot was, what, about this long,
10 feet long.
low velocity. I think there was at least 3 elbows.
4 or 5 elbows, actually.
By the time we stuck it up on there, they were able to run this exhaust fan, ECM motor.
Overkill.
By the way, this is a good point. When you don't know exactly where you want the airflow to end up, and sound is one of the drivers, when you order any little exhaust fan, get the little manual speed adjustment. In the old days, we had a rheostat like this one you see here. Today, you're probably getting an ECM fan, and there's something that looks something like that, but it's got about 10 speed selector points, and you just dial it for the speed you want. What did we end up on?
40%.
They wanted to be exhausting as much air from the hot corner of the server room as they could, which did get the temperature down to where they wanted it to be. But they wanted to exhaust, you know, they were pulling air in from God in every place. This room wasn't, nobody ever sealed the conduit entering that room, so, you know, they had plenty of ability to pull air in. And they basically just dialed the speed down until it got to where the sound engineer was happy.
Yeah.
And we ended up at 40%. Now, we could have done the little cheap 1 elbow sound boot, and maybe he would have been down at 20% or 10%, but we wanted him to be able to do as much as they could. So sometimes this is not terribly scientific. Sometimes you're just kind of pulling it out of somewhere on your anatomy. And that's what we did. Okay. Oh, so we were talking about this. There's more to the story. 2 stories, fan coil, condensing unit for the ground floor. Well, what if they didn't want to have condensing units? What if they gave us a chase, and this is a rooftop unit? And so I got a return duct somehow getting up there, however it's got to go from the ground floor. So you're going to have a fair amount of ductwork to get from the ground floor to this unit, because you got to go through the second floor, right? So when you go into economizer mode, economizer is called because it's supposed to improve your energy economy. If you take a paper bag and you blow it up and the bag gets big, that's what you're doing to the building when you go into economizer operation, because when it's cool enough outside, we've talked several times about how ideally the supply air temperature is 55. Well, the simplest way to look at that with an economizer is that 55, 56, 57, whatever temperature air we need, if it's that temperature outside, we shut off the compressor and we pull in outside air through the outside air damper, and we don't take this back around and have to mechanically cool it. We're just using outside air because it's 55, okay? But when we do that, what are we doing to the pressure on this floor? We're blowing it up like that paper bag, aren't we? So how do we, you know what happens if we do nothing else? The doors pop open and whistle like a mother, right? And that's not what we want. So we have to manage that pressure situation down here somehow. So the very simplest way to do an economizer is called barometric relief. Why are we, and we're going to use this term a lot, why are we calling it relief? What are we relieving? Pressure. Because we're relieving that supply air out, right? Okay, so the barometric relief in an economizer does something like this. Here's the rooftop unit, and here's that return opening we were talking about, and here's our outside air inlet with a screen over it, and shoot, maybe there's even a filter. When we go into economizer mode, we've also got in here a damper setup. And these dampers close, and these dampers open, and now the return air does that. And these dampers, and I'm going to draw them here even though this is seldom exactly where they're at, those dampers open at the same time that these dampers open. So as you're relieving that air out, you're now able to pull in more outside air. And because we have some of the best test and balance people in the industry, I can guarantee you that every single time we install a unit with an economizer, they set it up so that the supply CFM is correct when we're in economizer mode. Now, that's what we were doing in 1986. You had what was called a dry bulb economizer. Dry bulb. You would set it for some outside air temperature, let's say 55. And when you hit 55, it would switch over to outside air. But it was adjustable. If you didn't quite need 55, I mean, the time of year you'd be using this, it's cooler outside, right? So maybe you'd get about 56, 57, 58. You'd find through trial and error, depending on how much solar exposure you had in the room, you'd figure out what temperature you would switch over to economizer, and that was what we did in the 80s. So then the next step was, we haven't done psychometrics yet, but there is a little symbol, a little h, which stands for enthalpy. What is enthalpy?
It's a measurement of energy. It's like how much energy there is in the
Total
air.
energy. See, this is sensible heat, what you'd see on the thermometer. It has no idea what the latent situation is. Is it dry as heck or is it raining? It doesn't know. But the enthalpy, if you measure the enthalpy, that is the mix of sensible and latent heat, latent having to do with the moisture in the air. So the thing in the 90s was switching over to enthalpy control instead of dry bulb. The problem there was that the sensors in the 90s were crap. The initial ones used animal hair. I mean, that was the very first ones. They just were junk, okay? We didn't probably get I don't know, when did we get a good enthalpy sensor?
I'm not the person to ask that question.
It was after Y2K. I'm going to say sometime in the aughts, probably. Today's enthalpy sensors are actually pretty good. They're reasonably accurate, and they don't just last 6 months. I mean, they're reasonably good. So there's nothing wrong, and the energy code wants you to use an enthalpy sensor rather than a dry bulb sensor. And what that'll do is, if 55 is your nominal number that you like, that'll have an equivalent enthalpy level. Well, it's raining outside, it'll make it go colder because there's more moisture in the air, and so you probably wouldn't go to economizers quick. But if it's really dry outside, it would automatically jump you up, and maybe now it's 58, 59, 60 degree air, which may or may not work. That became part of the problem too. So then they got the programming to where it couldn't go, warmer than a certain temperature. I don't care what the enthalpy reading was. And again, this was a work in progress. It got figured out over time. Okay. So the barometric relief had to do with that damper. And all a barometric relief does is got a little weight. And one example of a barometric damper setup might have a little hangy thing with some weights that you screw on. That's a really simple, cheap one. There are better ones. But remember, we're blowing up the first floor with the economizer air, right? So you could come up with an equivalent pressure that you didn't want to get above here, and that would trigger the thing to open. So if you actually set the thing up well at startup, you could sort of equate the pressure that the return damper would go open with this. And if you did that, this damper becomes kind of unimportant, because what's the easiest path to escape? It's the shortest one, right? Now you'd have a damper here, but it didn't have to be low leak, it didn't have to be anything exciting, because if the return's coming up here, the pressure in the building will just push it out of there. And this little damper shutting is just help. Okay? That works really well on one-story buildings. Even if it's a huge building, it could be a bus terminal, you know, with a 30-foot high ceiling. On one-story buildings, that works great, because there's no pressure drop in a return duct, because you're pulling it out right at the ceiling, right? But on this two-story example, I've got a return duct going all this way, and it's probably not a nice, even, straight shot like that. It's got to get there somehow. So I might very well have, I don't know, pretty easily 3/10 of an inch, maybe more, even in a little rooftop unit. And the barometrics performance starts to get pretty sucky. And especially if it's not set right, or the little weights come loose, pretty soon your doors down here are popping open and whistling, and it's just no good. So 1991, Jim Holman, who was a sales engineer over in the office, and I came up with the first centrifugal power exhaust fan. Before that, though, on larger units, let's say that was a 15-ton, Carrier would give you a prop fan box that you would mount right here with a prop fan in it. So prop fans are weird. I don't know if you ever thought about this or realized it, but if we go a fan curve for a prop fan, and here's our CFM, and here's our static pressure, they have a very narrow band where they do anything. A prop fan won't overcome a ton of external resistance. You put, a prop fan at the end of a long duct and it'll hardly move anything. So it's like this. And a small difference in airflow equates to that. Now, did I do that backwards?
It's close enough. They get the point.
I think maybe I got to look at it. My brain just went dead. But a small difference in static makes a huge difference in air delivery with a prop fan. Yeah, so I know that first one's wrong, because it's huge differences in, what it is. It's almost flat. That's what it was, not vertical. It looks more like this. And a small difference in static is a huge difference in air delivery. So that actually works for a relief fan, because bear in mind, this air is plastic paper bag. We're blowing up, we're adding static here. So there's some push to help the prop fan. And so, if we were standing here in the 70s, even the first half of the 80s, everybody would look at a propeller relief fan and they would say, that's great. If one of these was in operation, you could hear it 3 buildings away on the lot. They are louder than shit. So that was one problem. Another problem was they couldn't overcome very much static. Carrier recommended that 15 tons and larger, you use that prop fan thing instead of a barometric, even on a 1-story application. Too much air to move. And the issue was the size of that damper opening, they couldn't make it big enough on a 15, 20, 25, 30 ton unit. There just wasn't physically room to keep the velocity through it low enough that there wouldn't be a lot of static. So they recommended it needed the little fan assist. But 2 things were happening by 91. One was people cared more about performance and sound. But the other thing that was happening was that by 91, variable speed drives had been around for a while. And so what Jim and I put together, and then had our curb and economizer manufacturer that we used build for us was a slip-in housing that would slip in to the side. You take the panel off, you'd slip it in, and what you had was a centrifugal exhaust fan and a little variable speed drive, and you'd put a pressure sensor down on that bottom floor, and it was a centrifugal. So it's quiet, and it would work off of the pressure, and you'd set it for whatever pressure you wanted to maintain. And pressure sensors usually have what's called a reference. What's a reference?
Baseline.
Baseline, yeah. Typically, if you're controlling off, there's two situations. One, you might be just reading the pressure in the pipe or in the duct. But the other one, you may be comparing it. And we would be comparing it. So this pressure sensor would be reading the pressure in here, and it would also have a little pickup tube right there on the roof. And so you were comparing the ambient pressure with the pressure inside the building. And that differential is what you wanted to keep under control so it didn't blow the doors open and whistle. Okay? So that was, in little units, the first centrifugal exhaust fans. And we cleaned up for about 3 years till Trane figured out how to build one and offer it. We were the only guys. You got it specified with a centrifugal exhaust fan, you were buying it from us. I don't care if it was 10% more money, 15% more money. You know, we were salesmen, right? That's how we were. So that is a centrifugal relief fan. And you'll find centrifugal relief fans now all the time. But that's not the only way to take care of pressure relief. There's also an evil way. And east of the Hudson River and north of New Jersey, in the city of New York, and in little parts of Chicago, instead of doing that, they use what's called a return fan. Although I think most of them have figured out it's not the optimum. So I'm going to draw this as though it was an air handling unit. Here's my air handler fan, and the duct comes out. And I've got a cooling coil. And I've got a filter. And then I've got my economizer section. And my economizer section has outside air that comes in through some dampers. And it's got some return air that comes in through some dampers. And it's got relief air. That's not the traditional setup. Here, let's do it this way. Here's return air. Here's exhaust. And this is your mixed air. This is simplified. So this, if you were going to use a relief fan, you'd have a fan here someplace blowing air, probably on the roof. You could mount it there. You could put it there. But with a return fan, what they do instead is they put one here. They have very similar logic for the fans. But what they do is they try to take return air and they are powering the return. With the relief fans, we were powering the exhaust, the relief. But a return fan powers the return. Why would you do that? There's one really good example. Almost every hospital you see does it this way. Why is that?
Air changes.
Well, it's not air changes.
Is that for bigger equipment, you were saying?
Yeah, usually. But why are we powering the return air?
You need to move the air faster.
More pressurization of, make sure you
It may need help.
They pressurize the spaces.
You want to filter that existing air.
Do hospitals use ducted returns? The short answer is yes. Because they want no cross-contamination between rooms in some ceiling. So every space is, that's a little bit of an exaggeration, but it's more or less true. Every space is ducted return.
What's your balancing act?
You're pulling a lot of static pressure resistance, and those are, that ducted return system from every room is going to have balancing dampers. Test and balance in a hospital, or test and balance with a real big return system is twice the money as test and balance in the normal air conditioning application, because you have to balance the return as well as the supply, because you've got a certain amount of air that's supposed to be leaving every room. Okay? And so there's a lot more static pressure. And that is the legitimate reason to use a return fan, is you've got an extensive return duct system. Okay. In New York, they liked to apply that to everything, and that was stupid, but that's what they did. So, I was going somewhere with that. Return duct. Oh, control. So there's a company, I don't think they're even still, is Air Monitor still in business?
Yeah.
So they came out in the 70s with a system that would track your supply fan, or it would control your return fan by tracking your supply fan. In theory, that was supposed to work well. It didn't. The supply fan needs to be controlled to maintain duct pressure, to get air to all these things, right? We already talked about how you control a supply fan. But how do you control the return fan? Because back in the day, they both would have had inlet vanes. Now they have variable speed drives. But how do you control a return fan in a... See, the relief fan was easy, right? We looked at the pressure in the lobby, we compared it to the outside, and it was simple. Not only simple, but it very seldom went bad because it was simple. Simple is good. How do you control a return fan with an extensive duct system? What signal do you give it?
Slightly less than the supply delivers.
Okay, slightly less. What do you mean by that?
It's all done by static.
Where are you going to measure slightly less?
That's return.
So, it's too bad Alan walked out. Alan is the single most opinionated individual I know when it comes to where do you measure the static to control a return fan. I'm not going to get into that heavily today because frankly I have to draw the picture and figure it out every time I do it too. But Alan is very opinionated on this. All you have to do is say, Alan, how do you control a return fan? Where do you measure the pressure? And he will, depending upon his mood and how much time he has, he will launch off into story after story of where they did it wrong. But he's very good with that, I'm telling you. He is one of the best at figuring out what to do about it. Okay, now we're going to move off of building pressurization. Are there any questions about anything we've done so far before we move to... Okay. If you got anything, just yell at me. It's not a problem. Does anybody know what this stands for?
Dedicated outside air system.
Outside air.
Dedicated outside air system, yes. So, what is that? What's a dedicated outside air system?
Pressure.
Okay, so Mark just used a term. I want to highlight this. We used the term in code. In code, the term fresh air was used until about the 90s. And then we replaced it with outside air. Does anybody have any idea why we quit using the term fresh air?
It's not necessary.
You might be in a temperature inversion and that outside air is worse than the air in the building, right? And that was the real world in Los Angeles a lot. So, yeah, but the point is valid. You got to bring in the outside ventilation air, okay? What might be in a unit usually up on the roof, that's bringing in outside ventilation air? What might be included in that package? No economizer, because it's 100% outside air.
Humidity control, cooling and reheat.
Could be some cooling, could be some heat. What else? There'll be a fan, right?
Sure.
Auto exhaust,
There better be some filters.
subcooling, okay, bypass.
That's probably most of what's there. Is we might have cooling, we might have heating, we will have filters, we will have a fan. Why do I say we might have cooling and we might have heating?
Pulling outside it.
What is this unit sending its air down to?
Could send it down to air handlers, which are doing cooling and heating.
Other air conditioning units, right? It could be a water source heat pump, it could be an air handling unit, it could be a fan coil unit, it could be anything. Why? I never heard that term until 20 years ago. Do you think we didn't have it before? What has brought on the need for this to be a specific thing?
Code requirements.
VRF.
All of those answers are right. Let me tell you a little bit about VRF before we move on. Back in the day, you would have a building, and it would have chilled water fan coil units in it. And if it was 4-pipe, it'd have hot water fan coils as well. And you'd have some supply fan up on the roof. Wouldn't have cooling, wouldn't have heating, it'd have a filter. And it would bring air down, distribute it, and it would drop some air off right behind this fan coil. And that was supposed to be balanced, because you were supposed to be able to make sure that you had the code required engineer design CFM for every fan coil that was outside air, because there was a ventilation air requirement. Maybe it was, depending on the time, it might have been 5, 10, or 15% were the typical numbers, depending on how far back you go. So we're putting our outside ventilation air in at the back of the fan coil unit, and at some point along the way the code said, no, just dropping it off at the back end isn't good enough, you have to hard duct it into the back of the end. Okay, so we'll do that. And we got to balance it. Chilled water and hot water work great for dehumidification. And you can see built in now, we were relying on this cooling coil to handle whatever heat and cooling load came with that outside air, right? It was all the cooling was being done right there. Chilled water does great, because let's say you were using 42-degree chilled water. You're using 42-degree chilled water probably year round. It's not a big deal, and 24/7, unless you were resetting it, and you could reset it a little. You quit dehumidifying at about 47-degree water, roughly. But more or less, you're using about 42-degree water all the time, and it works. VRF doesn't do that. VRF is and we'll talk more about it in the next series when we talk about mechanical refrigeration. But you've got a cooling coil, and you've got liquid refrigerant that's coming in, and after it goes through the expansion valve, design conditions, it's about probably 42 degrees. So far, this looks just like our chilled water fan coil, only we're doing it with refrigerant. But if you look at the energy efficiency ratings of VRF, they're unbelievably high. In fact, when they first started being published in the US, we just all called them liars. If the standard residential size condensing unit split system had an SEER of 14, the VRF equivalent would be like 18, 17. No way. We just knew that all of those people from across the Pacific were lying about the ratings because there's no way. I mean, the physics just wouldn't permit it. But there was something we didn't understand. What VRF does at low load, when you're down at, let's just say, 30% load, there will be some minimum CFM that will come across here, and it's probably somewhere in the 30 to 35% range of nominal. But what if you got even less load? You could have this fan cycle, but in commercial applications we don't do that because you're supposed to be continually delivering outside air. So we get down to whatever the minimum CFM is, call it 30%, but the load goes down and it's only 10%. What do you do? If this was chilled water, you'd keep throttling back on that 42-degree water and you would be barely trickling any in there. But to get their 18 SEER ratings, what VRF does is start lifting that temperature to have less lift on the compressor. And when you're down at your minimum airflow and the load keeps going down and you've only got 10 or 15% load, you're probably up around 60. What temperature did I say you probably need to do more or less, kind of sort of, to do any dehumidifying?
47.
So there's a fire station down on Balboa Island designed by a guy who didn't understand that. He put VRF in the fire station. He's got a DOAS unit just like that one that does not do heating or cooling. Fire stations are occupied 24/7. People sleep there. Okay? And so it's 2 in the morning on Balboa Island. You're surrounded by the Pacific Ocean. It's dark. There's almost no cooling load. And you're not doing any dehumidifying. Can you imagine? You're surrounded by water. How muggy it gets in that room. And how the firemen bitch with some level of I mean, they're right. The relative humidity in that place gets to be like 80%. What we did about that, and I veered off, but it'll get us back to the DOAS conversation. What we did about that is there's, 16 fan coils in the building. VRF has what's called a dehumidification mode. And you can pop it into full cooling, and that's what it'll do. And we ended up having to program about 3 at a time, doing that for like 10 or 15 minutes, moving around the station so that each fan coil spent 10 minutes, 12 minutes, 15 minutes in full dehumidification mode and then switched back to normal operation, just to keep the humidity level down, somewhere between 50 and 60%, which is probably muggier than somebody who's a native here would think was acceptable for sleeping. Maybe if you get the room cool enough. So VRF doesn't work the same. What should have happened, and this gets us back to DOAS, and anytime you do VRF, what should happen is this needs to have cooling. And the reason it needs to have cooling is so that you can knock some of the moisture out of the air before it goes down to the fan coils. Because if it's a VRF fan coil down here, at low load it won't dehumidify.
Yeah.
Now in normal office applications, it doesn't matter. Classrooms, it doesn't matter. It's not a big deal. But anything that's going to be occupied low load, at night, take your pick, you need cooling up here. And of course, our state energy code doesn't get worse and worse, it gets better and better in terms of efficiency numbers. And so the games that get played with suction temperatures, the temperature of the liquid entering the coil, keep getting to be more and more involved. And so as time passes, the need to be able to knock some moisture out up here gets to be bigger and bigger. Now, I told you that coming out of this thing, usually we want 55-degree air. What temperature would you guess we want coming out of this in the summer? Well, anytime.
70?
70 is a good number. Why? Why wouldn't we make 55 degree in the summer when we need cooling?
Cool it twice.
Well, if it's DX, you don't want
Not enough load.
too cold of
Condensation.
Well,
Too much condensation.
obviously, and we'll get into this mechanical refrigeration too, obviously whatever your condensing unit is that's making your DX cooling, it's got to be able to unload down to like
Summer,
nothing.
Dew point fire too.
I heard dew point. You don't want a bunch of condensation in here. So unless you're going to insulate this entire duct, and traditionally it wasn't. See, if this is just a filter and a fan, do you need to insulate this duct? Maybe the portion above the roof just to keep it from heating up, you know. But short answer is no. This is an outside air duct. You didn't insulate it. And as long as you don't cool it down below the point where you'll get condensation, you don't need to. Now, I freely admit that I can't anticipate every single case. There may be a time when you need the extra cooling from this thing to make the rest of it work. But if you do, you're going to have to insulate this duct like it was a supply duct. And so generally speaking, the term we want is we want neutral air from a DOAS. And the same thing in the winter. If it's 45 degrees outside, 70 is also a good number, because that's approximately the temperature that you're maintaining in the room. Okay? DOAS. That fire station was a real good learning experience for us. That was only the second project I'd run into where they had a low load humidity problem, but it was the classic example. And I'm sure the guy who designed it just had no clue, because most of the air conditioning reps that sell VRF, I don't know if they know this or if they just didn't tell you. Yeah.
How did you guys correct it then? You said it was a VRF, right?
Well, we set it up controls-wise to do full dehumidification and move.
Like 10 minutes in a zone.
Yeah,
And then it switched
there's
to
like
zone.
16 units or 15 units, and there were 3 at a time for like 15 minutes, 10 minutes each.
It just popped throughout the station right.
And all that did was help remove moisture.
Made it comfortable.
And that was like heat recovery VRF? So the
Yeah.
heat and cooling?
Okay, we pretty much beat airside to death. Does anybody have any airside related questions? We talked about air distribution in the space. We talked about the Coanda effect. We talked about where do you locate the temperature sensor or thermostat. We talked about a lot of stuff. We've wandered all over the landscape. Any questions?
I don't know if it's a question, but we had a problem once where the server room was, I think they didn't duct it correctly because they had 2 units in the server room, and it was more like half the building, half the room was done by this one and the other half by that one, rather than like intertwining the supplies.
So if I use the expression hot aisle, cold aisle, does everybody know what I'm talking about? So this is like the golden rule of server rooms. You've all seen servers, right? They have a muffin fan at one end, and they push air or pull air, but one way or the other, they take air through the circuit boards and the transformers and everything else that is involved in a server. Remind me, is it pulling it through or pushing it through? Pulling it out,
Pulls it in to push it out the back.
but which end is the fan on? On the out the back or in the front?
The back. Well, actually, it could be both.
Yeah.
Normally it's not the back.
I seen it in the back.
So let's draw it as though, and I also heard, yeah, it could even be both. But let's just say that we've got the little muffin fan, little propeller fan on this end, and it's blowing this way, and it's sucking air through to cool the server, okay? When you've got a server rack and you've got a ton of these, do you have them blowing different ways, or do you set them all the same?
You should set them all
They're
the
just
same.
all the same, yeah. And the why that is the importance in server room design. What you want to have happen is you want to concentrate the heat in one place. So if this is my server rack, and it goes down here, and it's got, I don't know how many servers, shelves, and it's full of servers here. And I'm standing here in this aisle, and I'm looking at all the little muffin fans, because they're right there, blowing in my face. Am I standing in the hot aisle or the cold aisle? Hot aisle. And why am I standing in the hot aisle? Because the air's going this way, right? And it gets heated up. And I'm standing there and it's blowing in my face. So, and now we're talking server rooms 30 years ago. What you would do is you would put the cold air in on this side, the cold aisle, and then the little muffin fans would be drawing the cold air through, and then you'd put the return on that side. And if you had two, you probably were putting the cold into the middle, and you had them pointed, and you took the return from both ends. And if you had yet another row, what did you have to do? You had to put up walls. Because, and this is what you end up doing in an old style. There's still a lot of these that only do that, don't do any more than that. You could improve the efficiency if this is plan view, and I've got a bunch of server racks. If I create a wall, and hell, it could be anything to prevent air movement. It could even be plastic. I mean, if I create walls, I could make hot, cold, hot, cold, hot, and I conduct it appropriately. The rule of thumb efficiency difference is between 15 and 20% if you do this versus simply dumping it in here, letting the muffin fans blow it, and then sucking it out on this side. Now, 15 to 20% doesn't sound like a hell of a lot. You're probably thinking, okay, so it costs me more to run my equipment. The big deal is, what that means is you could handle a 15 or 20% bigger heating load with the existing. Because from the time blade servers were invented, these racks have just gone, in terms of watts per device, they have just gone nuts in terms of how much heat they give off. So if you can go into an existing one that doesn't have this stuff, which is mostly general contractor work, you might have to reduct, to make sure that you're putting the cold in here, and you're pulling the hot out of the others. But you get this, and of course, you're in the room, right? So you're going to have a door here in each of these so that you can walk around and have access and all that. But you can pick up easily 15% more server load by doing that, and maybe 20. That's the over time typical. Now we've had continued things happen, and the super hot chips today, you even bring cooling directly to the chip. The chip has a heat exchanger on the back of it, and you're bringing this little line of water or refrigerant to the back of the chip and directly cooling the chip. And in a brand new installation, what they typically are is a mix of this and direct-to-chip cooling. Because direct-to-chip cooling isn't going to get it all either. But if you're doing direct-to-chip, you can handle a lot warmer conditions now than you used to be able to. And that gives you the option of not cooling the air to 55 anymore. Again, it's about energy. You can also, if you've got plenty of water, you can do evap cooling now, or at least a substantial amount of what you're doing can be evap cooling. So there's lots of games to be played in data center design today. And given that data centers are the big bubble right now, only the Lord knows how long the bubble will go till it breaks. But until it does, you're going to see people doing all manner of different things out there. I find it to be very interesting. So, any other questions? Oh, if you're going to do that though, one thing I didn't mention, I suppose it goes without saying, you have to monitor the dew point in this room. Any data center. Because you don't want any scenarios where you could have condensation. Chips don't like condensation. And seriously. So you gotta be monitoring that, and your system's gotta be able to adjust to control that dew point. If it's raining outside, that will have an impact on the humidity level inside. Yeah.
So what ended up happening with that unit, because they didn't like serpentine, because it did have hot and cold, they were forced to run both units. And both units was way over capacity for that room. And it would short cycle basically, to the point where we got a call one time, the walls are sweating in the room.
Mm-hmm.
There was that much moisture because it wasn't running long enough to wring the moisture out. And when it cycled off, it would get redistributed back in the air.
So it's important to understand that there can be air distribution problems when there's not a refrigeration problem. There's plenty of refrigeration capacity. It was grossly oversized for if you're going to run unit and the backup unit. But they had to run both units because their air distribution was screwy,
Right.
and they had warm areas. So when we built Channel 11's TV station, that was the first Western Allied job that I walked when I went to work here in '94. And when we built that, the building engineer who had come from their old building and was actually involved through the whole commissioning process on the new one, it's kind of unusual, the way to do it. He had one of these thermometers he would carry in his pocket with the little round top, and the little pointer. And he knew from experience which servers would cause problems first. And every morning, once everything was starting to get up and running, he'd walk around, he would poke it in the server. And he told me, he says, this one can go up to 95 inside and I won't have a problem. He says, this one can get to 105. He says, and this one can get to 115. I said, what happens if it gets warmer than that? He says, we get snow on the TV screen and I get fired. I wish I could tell you it was more complicated than that, but in some respects, it really is not. I'll finish with one last little short story. When we did the Fox data center on the Fox lot, a jillion crack units, it was the old style data center. The last step that the electrical contractor was supposed to do was adjust all the ground fault breakers. That never happened. And so it was a preseason NFL game. I was actually watching the game on TV. And suddenly, snow on the screen because a condenser fan motor had burned out on a little condensing unit. And because the ground fault breakers were not adjusted all the way back to the main, that trip caused the main breaker for the whole distribution center to trip. You layer these breakers for individual levels of response. And so that was never done. And as it happened, the guy who had been the facilities manager for about a year, when they opened it, they hired the guy who project managed the electrical. So we had snow for 20 minutes during an NFL game until somebody found the main breaker and reset it. And he got fired the next day. So when you hear somebody say, we'll get snow and I'll get fired, that is how that works. Ta-da.